Good morning. In today's session, we will discuss about damped oscillations. Okay, what is meant by damped oscillations? What is a damped harmonic oscillator? Like that. Okay, in actual practice, when a body undergoes oscillations, that is, when a body is undergoing oscillation, definitely its motion will be affected by various types of dissipative forces. Dissipative forces means something like frictional forces. And because of the presence of these dissipative forces, what happens is that the total energy of the oscillator decreases continuously. So when the total energy of the oscillator decreases, what happens? Naturally, the amplitude of oscillation decreases with the time, and finally the oscillation will stop. Okay, that is when a object is in motion, say definitely frictional force acts, that we know. Similarly, if a body undergoes an oscillatory motion and if there is any dissipative forces, then what happens? The total energy of the oscillator decreases. As a result, amplitude of oscillation decreases with the time, and finally at a particular stage oscillation will come to a stop. Okay, such oscillations of gradually decreasing amplitude are called damped oscillation, and the dissipative forces are called damping forces. Now, such an oscillator that executes damped oscillations are called damped harmonic oscillator. Now, this damping force, it will act just like a restoring force with magnitude proportional to velocity of oscillator at that time, and it can be expressed as minus gamma dx by dt. That is, the damping force is expressed as minus gamma dx by dt, where gamma is the damping coefficient. Now our next aim is to derive a differential equation for a damped harmonic oscillator. For that, we have to consider two factors that acts on a damped harmonic oscillator. One is the restoring force given by minus kx, and the other is the damping force that we have just discussed now, which is given by minus gamma dx by dt, where gamma is the damping coefficient. Now, taking into consideration these two factors, the equation for a damped harmonic oscillator is given by m d square x by dt square. What is it? Mass into acceleration. That is, mass is m, acceleration is d square x by dt square. So mass into acceleration is nothing but force. That force is equal to which are the forces? Restoring force and damping force. Restoring force minus kx and damping force minus gamma dx by dt. Now you take all the terms in the RHS to LHS and then divide that throughout with the m. Okay, then you will get an equation like this. That is, take all the terms in this right hand side to left hand side, then divide what you have obtained throughout with the m. So you will get equation like this. Here d square x by dt square is kept as such. Gamma by m is replaced with 2c, and k by m is replaced with omega 0 square. Okay, here this 2c, that is gamma by m, here c is the damping constant and omega 0 is the natural frequency of the oscillator. Okay, so now we are going to solve the equation of a damped oscillator. For that, we will assume a solution of the form x equal to a e raised to alpha t, where a and alpha are constants. Okay, so this is your equation for a damped harmonic oscillator. What is it? D square x by dt square is equal to 2c dx by dt plus omega 0 square x equal to 0. Let us assume a solution of this equation of the form x equal to a e raised to alpha t, where a and alpha are constants. Now, just differentiate this equation x a raised to alpha t with respect to t. So, x will be dx by dt. A is a constant. Then what is the differential of e raised to alpha t? Alpha e raised to alpha t. So, this will be alpha e raised to alpha t. Once again you differentiate, that is d square x by dt square. Again it will be alpha square a raised to alpha t. So you have got expressions for dx by dt, d square x by dt square, and for x. Okay, so substitute all these values in the equation 36. Okay, so in place of d square x by dt square, what you can write? You can write alpha square a raised to alpha t. Okay, now in place of 2c is kept as such, in place of this dx by dt, what you can write? You can write alpha a raised to alpha t. Okay, so 2c alpha a raised to alpha t. Then omega 0 square x, instead of x you can write a raised to alpha t. So you have found assumed a solution x e raised to a, x equal to a raised to alpha t, differentiated with respect to t dx by dt. Again you differentiated with respect to t to get d square x by dt square. Now you just substituted those values in equation 36 and you obtained an equation like this. Okay, here divide this equation with the common factor. What is it? A raised to alpha t. Divide this equation throughout with a raised to alpha t. So you will get an equation like this. Now this equation is a quadratic equation in alpha. Remember the equation that we have studied in lower classes, ax square plus bx plus c equal to 0. Here what will be the value of x here? Minus b plus or minus root of b square minus 4ac by 2a, right? Similarly, in place of x you are having alpha minus b. What is your b here? 2c. Okay, plus or minus b square minus 4 into a is 1, c is omega 0 square. Okay, like that. Now on simplifying, you will get alpha as minus c plus or minus root of c square minus omega 0 square. So we can write the general equation, general solution of equation 36 as x equal to a1 e raised to minus c plus root of c square minus omega 0 square t. That is, first you take the plus sign. Okay, then plus a2 e raised to minus c minus root of c square minus omega 0 square t. That is, first you take the plus sign and then you take the negative sign, minus sign. Here take the common factor e raised to minus ct outside. Everything rest is kept inside the square bracket. Okay, now the a1 and a2 are constants and their value depend on the initial position and velocity. Now depending on the value of damping constant and natural frequency of oscillator, that is depending on the values of c, which is the damping constant, and omega 0, natural frequency of oscillator, there will be three cases. First, let us consider the case c greater than omega 0, that is when the damping constant is greater than natural frequency of oscillator. In such cases, when c is greater than omega 0, definitely the square root of c square minus omega 0 square will be a real quantity less than c. Now, in equation 38, you just replace this root of c square minus omega 0 square with the letter b. Then that equation reduces to, that is equation 38 reduces to this one. Okay, then rearrange the common terms here. So you will get equation 39. Now you can see that both quantities on RHS, right hand side, decreases exponentially with the time. That means motion is not oscillatory. Now the displacement, that is x, reaches maximum value. Then it, after reaching the maximum value, it will decrease exponentially to 0 without any change in direction. This type of motion is called overdamped or deadbeat or aperiodic. That is, first the displacement reaches a maximum value and then it starts decreasing exponentially and finally it reaches 0 without any change in direction. This type of motion is called overdamped or deadbeat or aperiodic, and this occurs when c is greater than omega 0. That is, when damping constant is greater than natural frequency of oscillator. Now let us consider the second case, that is when c square equal to omega 0 square. In such cases, that square root of c square minus omega 0 square is not 0. Instead, it will have a small quantity, say h. So, replace that term, that is root of c square minus omega 0 square, with the small letter h in equation 38. So, equation 38 will reduce to like this. Now, you just assume that e raised to ht equal to 1 plus ht and e raised to minus ht as 1 minus ht. Okay, now substitute that value in this equation. That is, in place of e raised to ht, write 1 plus ht, and in place of e raised to minus ht, write 1 minus ht. And on rearranging, you will get this result. Or after that, it is enough that you write this equation straight away. Okay, e raised to minus ct within bracket m plus nt, where m is a plus a2 and n is a1 minus a2 into h. That is enough. Here, what happens to displacement? It increases initially. Okay, and as time progresses, the term e raised to minus ct will become dominant. So when that e raised to minus ct becomes dominant, the displacement which initially increased will now reduces to 0 within a short period of time, and finally oscillation will stop. This is a case of critically damped or aperiodic. This type of oscillatory motion is called critically damped or aperiodic. That is, displacement initially it increases, and as time progresses, the term e raised to minus ct becomes dominant. As a result, displacement decreases to 0 in a very short period of time, and finally oscillation will stop. This situation is called critically damped or aperiodic, and this occurs under the condition c square equal to omega 0 square. Okay, now the last condition, when c is less than omega 0. If that is the case, then the quantity within the square bracket, that is root of the quantity within the square root, that is c square minus omega square, will be complex one. Okay, so equation 38 will now become x equal to e raised to minus ct a1. That is, you just, instead of this term, you write that term as j omega. Okay, so it will be e raised to j omega t plus a to e raised to minus j omega t. Okay, now e raised to minus ct is common. Then a1 is written here. E raised to j omega t is cos omega t plus j omega t, because there is a formula like this. That is, e raised to I theta equal to cos theta plus I sin theta. Here your theta is omega t. So, e raised to I omega t will be cos omega t plus j sin omega t. Okay, here it is given, instead of I they have given j. So, you write j. Okay, similarly, a plus a2, what is e raised to minus j theta, or e raised to minus j theta is nothing but cos theta minus j sin theta. Here your theta is omega t. So, that substitution you have to make. Then rearrange the common factors. So, you will get it like this. That is, grouping cos omega t terms together and sin omega t terms together. Now, take a1 plus a2 as a0 sin phi and a1 minus a2 as a0 cos phi. Now, make that substitution in this equation. So, this equation will reduce to this one. Okay, that is x equal to e raised to minus ct is kept as such, or a0 is a common factor, it is taken outside. Sin a cos b plus cos a sin b. Here your a is phi and b is omega t, that is sin a plus b, that is sin omega t plus phi. Okay, then a0 is common, take it outside. E0, e raised to minus ct is there, then sin omega t plus phi is kept as it. Okay, so this equation represents an oscillatory motion with amplitude a0 e raised to minus ct and time period t equal to 2 pi by omega. Here it is equal to 2 pi by root of omega 0 square minus c square. amplitude of oscillation decreases exponentially with the time. So you call that oscillation as underdamped one. So that is a condition for underdamped case. That is when C less than omega 0. So you have got three conditions, that is overdamped, critically damped and underdamped. C greater than omega 0 for overdamped, C square equal to omega 0 square for critically damped, and C less than omega 0 for underdamped. All these three conditions are plotted in this graph. Okay, so draw this graph also. Now there is a definition. What is meant by quality factor or Q factor? It is nothing but it measures the quality of a harmonic oscillator. Then its definition is it is 2 pi times ratio of energy stored in the oscillator to the energy lost in a period. It is a dimensionless quantity. If damping is less, then naturally the quality of the oscillator will be high. Okay, that is, it is having a high quality factor or Q value. Okay, so this derive the expression for a damped harmonic oscillator is a possible essay from this chapter. Okay, so when you are asked that question, you have to start from the beginning up to here. Okay, you have to mention the three cases: C less than 0, C square equal to omega 0 square, and C greater than omega 0. So if you read, you won't understand. So write the definition, the derivation in a paper. Okay, then you will understand. That is, understand and write each and every step, because I think there is nothing much difficult to learn. These are all simple integrations and just replacement and all. Okay, so nothing more confusing. The only thing is then you try to write it yourself in a paper. Okay, then you will understand. If you read, that will not be effective as that you write. Okay, so this is an important essay from this chapter, that is derive the expression for damped harmonic oscillator and explain the three cases along with the diagram. Okay, thank you.